Good morning, everyone. Welcome today for another talk of the series Next Value Talk. Today, the guest is Thu Le-Anh, a PhD student from Tsukuba University, who will talk us about a queuing system for machine learning in data center cluster. So thank you for your presentation.
Okay. Good morning, everyone. My name is Thu Le-Anh from Tsukuba University in Japan. And thank you for having me today. And today I would like to present our research. This is a fitting Google data chase with maps for analytic queuing system with set up policy that are motivated by power consumption in data centers. All right, so so my research has two main goals. And the first one, we aim to enhance system performance and power consumption in large-scale data centers. And my research interest is queuing models. So today we will focus on queuing model. And the second point is that we try to make the model more reliable. To do that, we will use Google cluster chase to fit and find out the appropriate input parameter distribution, because we want to overcome the limitation of queuing model in general. That assume input parameter for exponential distribution. But today, we would like to verify this assumption by using the real data. All right, so first of all, about our motivation. You can see here, this is the Meta data center. As you might know, nowadays the adoption of AI is the expansion of data centers. So that's the reason why power consumption in data center is increasing rapidly over recent years. And all right, so you can see in the figure 2 that this is the electricity 2024 analysis and forecast to 2026. And this figure shows that in 2022, the power consumption in data center AI cryptocurrency was about 460 terawatt hours. And in 2026, it will be 1,000 terawatt hour in worst case, and at least 600 terawatt hour in low case. So although data center consume a huge amount of resources or energy, in data center, servers are typically utilized only 10 to 30% of the time, and during the idle period, they still consume around 60% of their peak processing workload. So a very simple and natural solution is turning on idle server. And it's very well-known policy, we call it on-off policy or on-off model. So next, I would like to explain you more about the on-off model. You can see here, in this system, each server have 3 modes: off, setup, busy or active. So in this system, when a job arrives to the system, an off server will be set up. And after setup time, it becomes active and will take the customer to serve. And one important thing of this model is that if an active server completes the service before the setup process ends, the server will take another job in the head of queue to serve. So at that time, the setup process will be interrupted. So that means we no need to set up more server than needed. All right, so this is about the on-off model. So due to the application of on-off model in data centers, up to now there's many study about it. And I want to show you here more recent paper. In the first paper, the authors considered MMC setup queuing model and some variants. And they propose recursive renewal reward method. And this method is quite similar to matrix analytic method. However, they no need to calculate the R matrix. But they have a reward function. So for monitoring, we can read this paper. And the second paper considered the same model as the first paper, but they adopt generating function approach. And they achieve a low computational complexity is only OC square. So all the papers show that verify the effectiveness of the on-off model to save energy. However, we see some problem because all the paper consider MFC setup is an MFC setup giving model. So that means they assume that inter-arrival times follow exponential distribution. And this assumption may unrealistic. So today we come up with the idea that validate this assumption by using the real data to test if exponential distribution is good enough. All right. So about the method, we take two main steps. The first step, we aim to find out a appropriate inter-arrival time distribution. To do that, we propose some distribution and we fit it with the real data, and then we select the best fit at the data level. And after we know the best fit at the data level, we will take the second step that we determine the best fit at the system level when we use the result from the first step as the input of the model in the second step. And then we measure the system performance of our setup giving model. And then we find the best fit at the system level. All right, so for the first step, data level fit, we will cross the trace version 3. This data is available and you can access from this GitHub link. And this data combines by 8 Google data set from 8 Google data centers. And about the method, we use two fitting methods. This is the MOM, the method of moments, and the EM, expectation maximization method. Because this method, MOM is very simple and it's on only the moments. And so it's very fast. On the other hand, EM algorithm is we need full trace, and we based on the maximized likelihood, it's on a likelihood function. And so it's slower, much more slower, but has high accuracy and can handle higher order. Right, so for the two methods, we use both tools that is available in GitHub. We can download and install to PC. It's very convenient. All right, so right, so very first check we use MOM method, and here I want to show you the result for a cell A. We have 8 cells from Google data centers, and for cell A, we have very first check here. We want to check if the exponential is good enough, and we have the log linear scale in the figure 4 and the log scale in figure 5. And it's very clear that exponential with the green curve is very far from the trace, but hyper-exponential is fits the trace very well for the log linear scale. And for log scale, we have the same chain part, and exponential is still worse, and hyper-exponential is better. However, for the body, we see it's still quite far from the trace. So that suggests that exponential distribution is not a good fit, and we need to check more complex distribution. All right, so next, so here we, instead of MOM, we use EN method, and we will test our more complex distributions, such as phase time distribution and macro arrival process. And you can see here we have it's clear that both freestyle and math close to the chain than hyper exponential. And we have the red and blue curve for freestyle, the green and pink curve for math. And clear that with the lower order, freestyle 2 and math 2 is quite far from the chase. But when we increase the order, here we have the freestyle 10 fit the chase very well. However, freestyle has no correlation, so math still a good choice. And next we have the result from cell B. So we have the same chance as cell A. However, for cell B, we only need freestyle 4 and math 4 as a good fit. And it should be noted that the higher order can improve the fitting. However, a very high order may lead to overfitting, and it's very complex and take time to conduct. So there's still a trade-off. So for freestyle, for cell B, we will choose math 4 and freestyle 4. Right. Next. One more thing, I want to show you the log likelihood and moments between the chase and freestyle and math. And once again, freestyle 10 and math 5 have good log likelihood, and the moments very close to the chase. And one interesting thing is that although math 10 has higher log likelihood than math 5, the moments of math 5 is close to the chain than math 10. So for cell A, we will choose freestyle 10 and math 5. Similarly, for cell B, we do exactly the same, and we see that freestyle 4 and math 4 is the split for cell B. All right, so one more thing we should consider is the correlation, because freestyle has no correlation. So now I just consider math. Once again, math 5 is much better than math 10, and correlation of math 5 is close to the chain of math 10. That means math 10 leads to overfitting. And for the cell B, the higher order, the better fitting, but still a trade-off. So for cell B, we will choose math 4. All right, so now we already have the best fit in the data level fit. So we turn to the second step, the system level fit. All right, in the second step, we aim to find out the best fit at the system level, and we consider the multi-server QA model with setup time, the model that I mentioned in the first section. And however, in step 2, we have new assumption that inter-arrival time will follow not only exponential but freestyle and math, and the parameter alpha and matrix T for freestyle, matrix D0, D1 for math. We already know by the fitting in the first step. All right, so for model analysis, we use matrix geometry method. It's quite familiar with us, right? And first of all, we need to define NT. LT and MT is the number of active servers, number of jobs in the system, and phase of arrival process at time T. And then we have the stochastic process is T. And we need to define pi ijk. That is the probability that there's I number of active servers, J jobs in the system, and at the phase K of the arrival process. All right, for matrix geometry method, we have the work and net process with the generator Q like this, with a some matrix Q0, Q1, and Q-1. And here, I will show you more detail about this metric. For J less than C, C means the number of servers. So J less than C, that means the non-homogeneous part. We have the submetric Q0, Q1, Q minus 1 right here. I think we can skip this part. And for J larger or equal to C, we have the homogeneous part and the submetric Q0, Q1, Q minus 1 here. Right, so for matrix geometry method, we need to find out all pi I. This is the steady state probability vector that system has I jobs. Once we know all pi I, we can find out the Q length and then the mean response time. Right, so we will use this part to turn to the result. Oh, all right. So here I want to show you the mean response time model, and here we have the result for the simulation for the chase, and both simulation and analytical result for the case with exponential, hyper, and math for interarrival times. And here it's clear that exponential is very far from the chase, and in the worst case, and however, free time and math is much better, and especially math close to the chase, and this is the best result. So that means although free time must PDF very well, that I show in the data level fit. Math 5 is the best fit at the system level. So this suggests that moments and correlation is very important and the key factor in fitting. And here we have quite similar result for cell B. It share the same chain, and Mark 4 is also the best fit in the system level. And exponential distribution still far from the chains, and the worst is the worst case. Right, so we want to consider more about coefficient of variation. So here I want to show you all the distribution. This is the deterministic, length, exponential, and hyper-exponential for cell A. And you can see here, the deterministic with coefficient of variation is 0. It's the worst case and very far from the chase. And when we increase the coefficient of variation, it's more closer to the chase. And the best case belongs to hyper-exponential, because the chain have very high coefficient of variation. It's a 1.83. So once again, when the number of server is small, the mean response time is very sensitive to the coefficient of variation. However, when we increase the number of server and the number of server is large enough, so nothing changes. So to sum up, we can see both moments and coefficient of variation and correlation plays a crucial role. All right, so we have the same result for cell B. We also have the hyper-exponential is the best case, and deterministic is the worst case for cell B, similar to the result of cell A. All right, so to sum up, we can see that the data is very good and they have a very heavy long tail. So that's why exponential distribution is not enough, but we need a more complex distribution such as phase time and math. And one more thing, with a few server, number of server is small, mean response time is very sensitive to the moments, correlation, and coefficient of variations. However, with when number of servers is large enough, we only need to match mean and coefficient of variation. This is because, as I show you later, hyper-exponential is good enough. All right, so to sum up today, I would like to give you a better understanding of the system behavior based on the data analysis on the Google cluster trace, and that leads to a data-driven approach for queuing model. And it's still on progress. So for the future work, because today I just show you 2 cells from a cell from Google trace. So for future work, we would like to consider all 8 Google trace cells. And because today we only consider inter-arrival time, so in future, we should consider both service time. And this may make the model now complicated, but I think at least we can use simulation of this. All right, so that's all my presentation, and thank you for listening. And do you have any comments, suggestion, and question? Feel free to ask me. Thank you.
Thanks a lot for the we have time for any question or any curiosity, also from home.
So the traces, do they also have some data for the service time?
Actually, for inter-arrival time is very straightforward.
Okay.
So this time, I think we can calculate from CPU mix.
Okay.
We have some.
So there's some data also about the amount of time required for each of those requests.
Yeah, but it's not straightforward. So we need more time to calculate.
And have you also estimated, how much energy, in the sense at least of how much server on time can you save with the setup and shutdown of services? So can you also?
Yes, I think I will. Okay. Because we care about the power consumption. So, but for this we need a power consumption function. So, yeah, but I will, because in our previous study we also consider bicycle model and we have a function for power consumption. But this work is still on progress, so I will add this.
I have one question, but it may be a dumb question. So, if I understood correctly, the idea is you have a queue of jobs, and these jobs are scaled according to their mathematical formulation. How can you ensure that there is no job that is always postponed?
Always postponed.
Postponed. I mean, if all of us submit a job, okay? If I understood correctly, the idea is we do not just execute in order these jobs, but we can schedule them properly.
Schedule job.
But actually, the jobs are executed in order.
Always, that's the question. So they are always executed in order. There is no reordering about our jobs in order to.
On the server, they have the one that are.
Okay, that was the question. I was just wondering if there was some sort of reordering, because it may be an idea to reorder the jobs in order to parallelize as much as possible, but then you have to ensure that one of the jobs is not staying idle.
I see. Yeah.
That was just a question. Thanks.
Usually, this mathematical approach works best for first come, first served type. So that's the basic, and then of course on that you can parallelize the execution, but you still preserve the order.
Okay.
Sorry, I didn't mention about this stuff.
Any other questions? Okay, so thanks again for your presentation. Thanks everyone for listening to this presentation. We will see the next
Thank you.
next week. So thank you.
Yeah, thank you very much.
Thank you.
Yeah.
What's the job?